Hello there, good evening. Some of you would remember that in the last video I made, I mentioned that I was wanted to look at Boolean algebra or binary logic. Now, what I've done, I'm able now to put those items together. What I want to try and do now is to actually show you what I have in mind. Okay, so bear with me while I bring the camera around. Okay, thank you again. Okay. Now, hoping that you will be able to see this, but I'm going to make sure that I keep it steady in a manner that it can be seen. Okay, so bear with me for a moment. Sorry about that. So okay, take me a little while to get it into frame. Okay. Now what I want to look at first is this section here first. Boolean algebra. Boolean equations can be simplified by either algebraic or mapping methods. Now, the algebraic simplification of logic functions is facilitated by the use of the logic rules, which are shown. Now, if you're dealing with logic systems, you need to first know the rules that applies to those systems. And that is important to understand. And here are the rules. A or not A equals 1. A or A equals A. Now A and A equals A. A and not A equals not. Now, don't worry about this too much just yet, because you will see how these comes into their own play when you actually look at the logic gates themselves. Okay? Here, A, open brackets, B plus C, close brackets equals AB plus AC. Okay? A or not equals A. A or 1 equals 1. A and 1 equals A. So whatever the value of A is, as regards to its binary or logic input, that's what the value will be, A. A and not equals not. A and B equals B and A. A or B equals B or A and B, open bracket, A plus or not A, my apologies, or not A, close brackets equals B. Okay, here B, open bracket, A or not A, close bracket, coming to B or 1, which will simply be B. Okay. Now again here, I simply again A or A and B equals A. Again, open bracket, A or B, close bracket equals A. Now here, A or not A and B equals A or B. A, open bracket, not A, or B, close bracket equals A and B. Now, not A or B equals not A and not B. Now, the dot is an AND function. Okay. And here you have again, not A and B equals not A or not B. Now let me just take this out a little bit to make sure that I can get everything in. Okay. Okay. Right. Now keeping that in mind, just turning the page over. Okay. Now, these here are logic. Let me make sure I can get it online on the camera. These here are logic gate symbols. Now, they are probably an additional gate symbols these days because there has been such a massive transition in logic gates. Their structure and their makeup is now tremendous. Now, that's an AND gate. That's a NAND gate. That is an exclusive OR gate. This is your NOT gate. Okay. That is an OR gate. This is a NOR gate. And purely here we call this the coincidence or exclusive NOR gate. Let me just go down and make sure that comes into play. Okay. Let's pull back a bit as well. We go back a little bit further. Okay, that we get everything into play. Okay. Now let me change. Bear with me while I change the page. Okay. Okay. Sorry about that. Now, as you know already, I don't really fuss about making mistakes or so forth. I'm not into perfection in any shape or form. Okay. So sorry about that. Bear with me while I try to get this on how I would like it to be. Okay. Thank you. And here we have Boolean. Draw a system of logic gates to perform the following functions. And that should be an S on the end. Following functions. A and B and C, or A and B and not C. Two, not A, B and B, or A and B, not A and not B, or A and B. Sorry, that should be no. Did I say, if I said something else, my apologies. So I keep forgetting that I'm dealing with logic gates at the moment and not a mathematical function. And again, here you have an A and B, or A and C completely knotted, and a similar thing applies in both cases here. So what we want to look at is taking these functions and putting them into a logic gate format. Okay. Let me just go a little bit to make sure that you can see everything that's on the sheet. Okay. Now, to get an idea of how this logic function works, sorry, let me just make sure I've got this in play. Okay, we get AND function. Now here I've used a simple switch system to show you the mechanics of this. Supply A to switch A, switch B. Now if I close switch A, the lamp will not light. No matter what you may do, that lamp will not light while switch A is closed. Okay? Now if I close switch B, now the lamp will light because A and B are closed. It has completed the circuit. Now if we go down here and we have a look at this as well, again we're using A, switch B. Now in order for the lamp again to light here, which F would be our output, we must have that switch, that point there now needs to come to switch 1, position 1, where at the moment it is in position 0. If we put it into position 1, then A and B will bring the lamp on. That means that there's a complete circuit, there's an output. So what we're trying to say here is that for an output to occur in a logic gate, you must have, based on the table, you can have it as one as an A or B input. But those A and B inputs in regards to the AND function must be at a logic 1. Okay? Bear with me for a moment. Okay, let me just get this in focus. Bear with me while I get this done. Okay. Now what we're looking at here is the exclusive NOR function using NAND gates only. Okay, exclusive NOR function using NAND gates only. Now what I've done here is simply to show you that we have a NAND gate here. We have input A, input B. Now those inputs can come from anywhere, but normally you'll find that the voltage in regards to a logic gate is always above 2.4 volts and with a maximum of 5 volts. There is a gap between 2.4 volts, which they call a not used voltage area. So anything above 2.4 is usable, but anything below that we consider to be a logic not. Okay, and I am just simplifying that overall. Okay. Now you can see here the output here is not A and B, and again here for the output at S using a NAND gate, we've got not A and B, not A and B, and A and B knotted again. That is your output function here, okay, in regards to this NAND gate. And again, a similar base here for in regards to this NAND gate as well. But you need to actually draw out these diagrams for yourselves so you can see how they come about, and do a bit of research as well for yourself also, because there are now a variety of integrated circuit systems that is brilliant, that does away with the building of these. Now, when this was done, we didn't have a variety of gates that we could choose from, but nowadays you do. And you won't need to build these, you can actually just buy them outright, okay? But I think it's important to remember where we were, okay, and where we're coming from in certain cases. Now here's what we call your truth table, okay? And you can see here that, let me just get in a little bit closer, okay? Now, let me read this first to you here, okay, first. Truth table for exclusive NOR gate made using NAND gates. Note, remember we are putting the output at Z through a NAND gate, so it will be inverted, okay? Note we have combined A and not A and B to give us S output, okay? Now here, you can see that these will be your input. So for, excuse me, sorry. And again here, input. Now, what this is telling you that if you have these two inputs, for not A and B, you will get a logic 1, output 1. For this stage, not input 0, where A is 0 and B is at 1, you'll get a 1. Where A is 1 and B is a 0, you will get a 1. But where you have two 1s, you will get a 0, because it has been inverted by the NAND gate itself, okay? And so on and so on, and this process will follow through. And you can simply take in your input at this stage, you can see the output for S, okay? Taking your inputs again, you can see the output for P. Again, in reference to your inputs, would also be applicable to Z. And again, input giving you your final output for F, okay? Now let me just pan out a little bit, make sure that I can get this all in, okay? See, I'm always trying to go back further, see if we can work. But when I look at my screen, I've got half of it blacked out. I have no idea why. I try to get rid of that thing that says say something. Yeah, it just sits there, say something, and it says nothing. Okay, thank you. Okay, let's move to the next slide. Now, let's just get this into focus, okay? Sorry about that. Bear with me for a second while I actually pick this up. Okay. Okay. Now, using other gates to perform other functions. Now here, you can see we've used a NOT gate, AND gate, and AND gate. Okay. And again here, input A, input B. These will be your inputs. Now there's a truth table created for this somewhere along the lines, and I believe I may have it on the next slide. But bear in mind, look at how the gates are set out. And this is using other gates to perform other functions. That should be functions. Okay. So let me just step back a little bit and go down. Okay. Now here you can see we have exclusive NOR function from this point to here. Okay. And you can see that we have the exclusive OR function, and that gives us what we need here as the truth table that tells us how we have achieved that OR function. Now you need to do some research for yourself. Draw out the diagrams, see what they've said. Look at the logic gate systems. You can actually acquire certain logic gates that will do simple functions for yourselves. Okay. Let me just go back a little bit, see if I can get this all in. Okay, I think that might just about do us. Okay. And again, this is using, let me just go up one bit, using other gates to perform other function. Okay. Now, SR flip-flops. The SR flip-flop is simply a term used in regards to set and reset flip-flops. Now, if you're dealing in electronics or binary logic systems, you will know what flip-flops are. But if you're not a layperson in regards to flip-flops, no point me trying to explain it to you. You will need to go away and read some information to understand what these flip-flops do. Okay. Now here we have set, reset, Q and not Q. Okay. Now the not Q here is we're going to take this as being this because Q is quite clear. It's set out already. Okay. And we have a truth table here. Okay. So you can see that when S is at 0, input is 0. When R is also in 0, Q is 0, and they're both at 0. They're still set, reset. Okay. They both have the same value. Now, what is interesting here is why we have 0 here, and 0 here, and 0 here, and 1 and output there. I'll get back to you on that. I'll say exactly why. But this will be your truth table outlay. Now I'm sure I've got probably have another acetate which gives me further information on this. But that I may have put this one first for a reason. But bear with me, I will get there eventually. Right, let's just have a look at whether or not I have got a more detailed information for myself. Now, these are, it's interesting because I did a lot of this in my agency electronics. But you know how long ago that was? I hate to tell you. I don't even want to mention it now, guys. Master slave SR flip-flop. Now, I'm not going to go into this just yet. What I'm going to try and do is to let you have a look at this, how this is made up purely. And normally there would be a function and an explanation as to how it actually works. But what I've done here is purely give you a diagrammatical view of the master slave SR flip-flop with a view that you should be doing some research yourself to find out what it actually is and how it works. And you'll find a lot of information now on this in regards to these things online quite easily. Okay. Okay. I'm going to leave that there for now. Now, remember, this is not complete by any means, and I will probably be adding to this in due course. And here we have, let me just get these out of the way first. Okay, thank you. Here we have SR flip-flop clocked. Now, I have information showing you how a clock system works, and I will try and bring that up next one I do. Okay, but these are again SR flip-flops, and they're going to showing you here how logic gates has been used to create them. Now there's a truth table for these. Okay, so bear that in mind. It's just that I've just shown you the logic gates first with regards to the flip-flop, and simply to introduce them to you overall. Let me just see if I can step back a bit to bring it all in. Nope, that angle is right. Okay, thank you. Good, okay. Now, using NOR gates only to produce the exclusive NOR and the exclusive OR function. Now you can see here that here, between here and here, we have created the exclusive NOR function. And between here and here, we've created the exclusive OR function. Let me just go up a little bit, make sure you can get all this in. I'm going to step back a little bit, and so we can get this in to play. Okay. Now, here we have the truth table showing you how that has been achieved. Again, remember your basic inputs, and by making certain inputs change the process, we can bring about a change in its output function. Okay. This is your truth table for this logic gate system. It tells you how we have achieved that by using other gates. Now I have a bit more to add to this, but our road run at the moment is to bring it purely as an introduction. Let's see where we go from there. But what it does do, it does leave you with an inclination to do a bit of groundwork for yourself to see how this would tie in, and how you yourself can actually, by applying a voltage to a integrated circuit, you can make it do almost anything or get a result from it. Use some of those gadget little electronic books. I'll show you one next time round when I actually can put my hands on it, because they're quite useful. Well, let me just step back a little bit and see if I can get all of this in to play. So bear with me. Yes, I think that's about it in play. Okay. Right. Thank you for your time. I hope you found this useful. I will add to this with more text and detail and giving you the process as to how a lot of this works. But for now, all I've done is to give you an introduction to logic gates or Boolean expressions. Okay. Thank you. Bye-bye.